Welcome to another Explainer. Today, we're taking a really fascinating journey from the deep, theoretical foundations of artificial intelligence straight into the driver's seat. We're going to look at how these massive AI models are built under the hood, and then transition right into how we can practically steer them using some incredible developer tools. If you've ever found yourself wondering how generative AI actually works behind the scenes and exactly how software engineers are building the next generation of applications with it, well, you are in the exact right place. But before we get our hands dirty with technical dashboards and lines of code, we really have to start by answering a fundamental, almost philosophical question. How do AI models actually think before they speak? It's so easy to see the magic when ChatGPT types out this fluid, human-sounding answer. But what is the actual cognitive and computational process happening just milliseconds before that text appears on your screen? That's the exact mystery we're unraveling today.
So here's our quick roadmap for this explainer. First, we'll hit the engine room. Second, human steering. Third, the practical dashboard. And finally, number 4, the next horizon. Let's just dive right in.
Okay, Chapter 1, the engine room, generative AI foundations. It all starts right here at the absolute lowest level, with a concept called embeddings. Essentially, embeddings are dense vector representations, or fixed-length arrays of numbers, that capture semantic relationships between tokens. Basically, during the initial training phase, AI models process unimaginable amounts of unstructured internet data and learn how words relate to each other. They map these relationships out into this massive, multidimensional mathematical space. So the model doesn't understand the word apple, like you or I do, right? Instead, it understands a highly specific array of numbers that places the concept of an apple mathematically close to words like fruit and tree and way far away from car or skyscraper. This right here is the absolute bedrock of how AI comprehends human language. Now, when we look at the models themselves, there are 2 main types of transformers you absolutely need to know. First, autoregressive models, like OpenAI's famous GPT series. These models read and predict the next token strictly in one direction, from left to right. Because of this forward-moving momentum, they are just absolute masters at text generation. Then, on the other side, we have auto-encoding models, like Google's BERT. These models look at context bidirectionally, meaning they look at the words before and after a specific word at the exact same time to understand the full context. This deeper understanding makes them brilliant for analysis tasks, like text classification or sentiment analysis. So a great way to think about it is a generative model writes the essay, while an analytical model grades it. So once you've built that model architecture, how do you make it smart, helpful, and above all, safe? Well, think of it like raising a student. First, there's pre-training. This is literally just handing the student an encyclopedia, feeding the raw model massive data sets so it learns grammar, facts, and basic reasoning. But a raw, pre-trained model, it can be super unpredictable and sometimes genuinely unhelpful. That is where alignment comes in, specifically a technique called RLHF, or reinforcement learning from human feedback. This is basically teaching the student good manners. By using actual human feedback to reward the best, safest answers and penalize the bad ones, we align the model to actually do what we want it to do, making sure it serves the user without completely going off the rails. As developers, we face a pretty massive trade-off when choosing which engine to use, proprietary versus open source. You can go proprietary like OpenAI's GPT-4 or Google's Gemini. These offer massive scale and just incredible out-of-the-box reasoning. But the catch is your access is restricted behind an API controlled by a single company. They're fantastic for general enterprise apps, though. On the flip side, you can choose open source models, like Meta's Llama. These are totally transparent, highly customizable, and driven by huge global communities of researchers. If you're a developer who needs to do very niche fine-tuning, or if you have strict data privacy requirements where the model literally has to live entirely on your own private servers, open source is absolutely the way to go. All right, Chapter 2, Human Steering, or as you probably know it, prompt engineering. And this is where things get really interesting. Because here is the undeniable truth. Even the absolute most powerful multi-billion parameter AI engine in the world is completely useless without a skilled driver at the wheel. So, how do you steer effectively? Let's talk about the core tactics for prompt engineering. First off, be clear and specific. Don't leave any room for ambiguity. Second, and this is a total game changer, assign a persona. Telling an AI, hey, you are a senior financial analyst, isn't just fun roleplay. It literally mathematically shifts the probability distribution of the model's vocabulary. It surfaces industry-specific jargon and deeper analytical frameworks that just wouldn't appear in a standard generic response. Third, use delimiters like triple quotes to cleanly separate your instructions from the raw data you're feeding it. Fourth, break complex tasks into explicit sequential steps so the AI doesn't get overwhelmed. And finally, you have to give the model time to think by explicitly asking it to lay out its reasoning step by step before giving the final answer. Why does that work so well? It exploits the autoregressive nature of the model we just talked about. By forcing the AI to generate its logical steps first, you are feeding it its own highly accurate context to build the final answer from. It drastically reduces the chance of hallucinations. These aren't just minor tips, they are literally the steering wheel and pedals of generative AI.
Moving right along to Chapter 3, the practical dashboard, the OpenAI API.
Before we can even think about making an API call, we need to talk about the fundamental currency of the entire AI ecosystem, the token. It's the basic unit of data processing and pricing in AI. You see, models don't actually read words, they read tokens, which represent pieces of words. A word like hamburger, for example, might be broken down into 3 separate tokens: ham, burr, and jur. Understanding tokens is absolutely vital because it dictates how much context your AI can remember at any one time and exactly how much your application is going to cost to run. And that brings us to a super important number, 1,000. When you open up the OpenAI API developer dashboard, you're going to see that pricing isn't calculated per word or per sentence or per request. It is fundamentally calculated per 1,000 tokens. And here is the kicker. You, as the developer, are charged for both the input prompts you send to the model and the output generation the model sends back to you. If you're building a tool that summarizes, say, massive, hundreds of pages long PDF documents, tracking and optimizing those 1,000 token batches is the absolute key to keeping your project financially viable. Now, when you're ready to build a truly agentic application, something that goes way beyond a basic chat interface, OpenAI provides this incredibly powerful workflow called the Assistance API. And it works in 3 distinct steps. Step 1, Assistance. This is where you define the AI's core role, its custom instructions, and the tools it gets to use. It's kind of like writing a formal job description for your digital worker. Step 2, Threads. This creates a persistent conversation session. It's basically giving your new assistant a desk and a filing cabinet so it remembers the entire chat history, meaning you don't have to resend the context every single time. And step 3, Runs. This is the execution phase. It's where you actually trigger the AI against the thread, asking it to complete a specific task using the context it has securely stored. And what makes the Assistance API so revolutionary is actual agency. These aren't just text predictors anymore. For example, the code interpreter tool allows the AI to write and execute real Python code inside a secure sandbox to do complex math, analyze CSV spreadsheets, or even generate data visualizations. It's not guessing a math answer, it is literally calculating it. Then there's File Search, which is a built-in retrieval augmented generation tool. This lets you upload your own proprietary documents, like company HR policies or private technical manuals, so the AI can retrieve and cite your specific private information instead of relying purely on its public pre-training data. Which brings us to Chapter 4, and I am so excited to talk about this. The next horizon, future models. We've seen what developers are building today, sure. But the architecture of artificial intelligence is evolving at just a breakneck pace. We are currently witnessing a massive evolutionary leap in what these models can do. Traditional large language models generate answers primarily based on learned pattern matching. They're incredibly good at predicting the next most likely word based on their training data. But OpenAI's new O1 model, it is fundamentally different. It uses reinforcement learning to actually think and reason before providing an answer. Instead of just blurting out the first word that comes to mind, O1 essentially argues with itself in a hidden scratchpad. It explicitly mimics human chain of thought reasoning, trying multiple approaches, breaking down complex math or coding problems, and actually correcting its own mistakes internally before it ever shows you the final output. It is a monumental shift from simple text generation to true complex problem solving. And that leads us perfectly to one final massive question to leave you with. Will test time training, or TTT models, ultimately replace the ubiquitous transformer architecture entirely? You see, transformers, like GPT, are incredibly powerful, but they require massive, continuously growing amounts of memory as their context window expands. TTT models represent this experimental new architecture that uses a machine learning model to encode data into representative variables called weights. What this means in practice is that their size stays remarkably constant no matter how much data they process. Imagine an AI that learns like a human. I mean, reading a book doesn't make your physical brain larger or heavier, right? TTT models do exactly that. They are highly efficient, they completely circumvent the memory bottlenecks of transformers, and they could very well signal the next massive paradigm shift in how generative AI is built. So what do you think? Are we already looking past the transformer? Thanks for joining me on this explainer. I hope it sparked some exciting new ideas for you, and I will catch you next time.